So, to get an AI to think deeply about a complex problem right now, you basically have to sacrifice your hardware.
Yeah, you really do. It's a huge bottleneck.
Right, like generating a 32,000 token reasoning sequence on a standard model, that requires nearly 28 gigabytes of memory just to, hold its train of thought.
Which is massive. I
Yeah.
mean, that immediately restricts any kind of deep AI reasoning to these massive, expensive data centers.
Exactly. But imagine if you could achieve the exact same level of sophisticated multi-step logic using just 9 gigabytes of memory.
Well, you'd fundamentally change the accessibility of advanced AI, right?
Mhm.
You'd be decoupling the depth of a model's reasoning from the actual physical constraints of its memory footprint.
And that is exactly what we are getting into today. Welcome into this custom deep dive. Our mission today is to unpack a brand new state-of-the-art research paper that delivers exactly that breakthrough.
Yeah, it's a really exciting one.
It's titled Memory Efficient Looped Transformer: Decoupling Compute from Memory in Looped Language Models, which is a mouthful. So we're just going to call it MELT for short.
Melt is definitely easier to say.
Right. And for you listening, whether you are building AI applications yourself or, just simply trying to understand where the technology is heading tomorrow, this paper is a massive signal.
Oh, absolutely.
Because it proposes this radical architectural fix to the memory bottleneck that is just currently paralyzing the field.
Yeah, and to really appreciate the leap that Melt takes, we kind of have to establish the baseline of how we currently force large language models to, reason.
Let's do it. Where are we starting?
So the dominant approach across the industry right now is chain of thought prompting.
Right. COTI.
Exactly.
Yeah.
You ask a model a difficult question, and before it outputs the final answer, it generates these intermediate thinking tokens.
It's literally generating words, right? Even if the user interface hides them from you.
Yeah, exactly. It's writing out text to work through the logic step by step.
It's like a student writing out every single step of a multi-part calculus problem on this limitless scroll of paper.
That's a great way to picture it. It works. The student gets the right answer eventually.
But the scroll gets absurdly long. And in the AI architecture, every single word written on that scroll it's eating up computational latency and VRAM.
Yes, you are directly tying the depth of the AI's thinking to the physical length of its output sequence.
Which obviously hits a wall.
Right, because writing out every step physically exhausts the available memory on the graphics card. So researchers realized they needed a completely different paradigm.
And needed to stop writing things down.
Basically, yeah. They developed this concept of latent reasoning using architectures known as looped transformers. And understanding this stepping stone is super vital before we actually look at MELT.
Okay, so let's unpack loop transformers. The paper focuses on one called RO, specifically RO 1.4b, right?
Yeah, a 1.4 billion parameter looped model.
And instead of that limitless scroll of paper, looped transformers do something that sounds, honestly, almost like science fiction to me.
It is pretty wild.
Rather than generating new tokens horizontally to think, they perform vertical reasoning.
Right, they recycle.
Yeah, they take their existing internal transformer layers and recycle them. The hidden states are just passed through that exact same architecture over and over again.
It's like the model sits there, closes its eyes, and just churns the information recursively inside its existing neural pathways.
Without writing a single new word on the page.
Exactly. It performs recurrence at the architectural level, and the results are, honestly, highly impressive.
Right, because a relatively small model like this 1.4 billion parameter one can punch way above its weight class.
Yeah, it outperforms standard, non-looped models that are nearly twice its size on complex multi-hop logic tasks.
But RO has a fatal flaw.
It does, and it comes down to its key value cache.
The KV cache.
Right, the KV cache is essentially the model's short-term memory.
Because even though RO isn't generating visible tokens to show its work, it still has to, remember what it thought about a millisecond ago to form its next thought.
Yeah, and standard loop transformers manage this using an append-only strategy.
Append only. Okay, meaning what exactly?
Meaning, for every single reasoning loop, the model saves a completely new KV entry. So if the model loops 10 times to solve a coding problem, the memory footprint goes by 10 times.
It scales linearly.
Exactly.
Yeah.
Think of the KV cache in this scenario as a physical receipt.
Okay, a receipt.
The model prints a receipt for loop 1, then it prints a second receipt for loop 2, and, tapes it to the first.
Right, right.
By the time it finishes deep reasoning over 100 loops, it has printed 100 receipts.
And the system VRAM is entirely exhausted. The cache register literally jams.
Yeah, the memory cost for deep reasoning just becomes impossible to manage, especially when analyzing really long prompts.
So if printing a physical receipt for every loop eventually jams the machine, I mean, the only way forward is to stop printing and start overwriting.
Which brings us to the architectural leap proposed by Melt.
Enter the MELT breakthrough. So how does it actually decouple the compute from the memory?
Well, Melt abandons the append-only strategy entirely. It maintains a single fixed-size KV cache per token and per layer.
Okay, so instead of appending a new state at every single iteration, it's doing what?
It mathematically updates a single latent state across all the loops.
Ah, okay. So instead of a receipt printer, MELT is using a dry erase board.
That is a perfect analogy, yes.
It has one fixed board. When it forms a new thought in the next loop, it just wipes away what it no longer needs and writes the new insight in the exact same physical memory space.
Exactly. But the engineering challenge there is determining what to keep and what to erase.
Oh, right. Because if the model wipes away a critical piece of logic from loop 2, I assume the entire chain of reasoning just collapses by loop 10.
Completely collapses, yeah. So to govern this updating process, Melt utilizes a learnable gated momentum mechanism.
Okay, a learnable gated momentum mechanism. Let's unpack the math of that element-wise gate.
Sure. So for every piece of data at every step, this gate actively modulates the hidden state.
It calculates exactly what fraction of the previous loop's information should be preserved, right?
Right. And what fraction should be overwritten by the current loop's new calculations. It acts as both the eraser and the marker simultaneously.
But looking at this, my immediate question is like, what about data decay?
What do you mean?
Well, if you are constantly overwriting the exact same tensor array 50 or 100 times, doesn't the original train of thought degrade? How does the model maintain stability over dozens of loops without the data just decaying into absolute noise?
That was the big question. And the researchers provide a rigorous theoretical analysis proving the spectral stability of this specific gating mechanism.
Spectral stability.
Yeah, they refer to it as establishing a gradient superhighway.
Okay, that sounds cool. What is a gradient superhighway?
Well, in standard recurrent neural networks, or really any looped architectures, you run into the vanishing or exploding gradient problem.
Right, as the error signals travel backwards through dozens of loops during training.
Exactly. They tend to either fade away to zero, which halts learning entirely, or they compound exponentially and just break the system.
But Melty's learnable gate is stringly bounded, isn't it?
It is. The researchers proved it keeps the spectral radius near 1.
Meaning the magnitude of the gradient is preserved? The signal doesn't die and it doesn't blow up.
Exactly. It shifts the burden of retaining information. Instead of relying on explicit, expensive storage, like printing endless receipts,
Right.
it places the burden onto the learned dynamics of the gate itself. So the gradient error signals can travel perfectly through arbitrary loop depths.
The inference architecture is beautiful. I mean, the math basically guarantees the dry erase board doesn't turn into a smudgy gray mess.
It does, but there is a massive catch.
There usually is.
Changing the fundamental architecture from an append-only receipt machine to an element-wise updating dry erase board completely breaks how we actually train large language models.
Because of the parallel processing?
Exactly. It introduces a severe parallel processing bottleneck.
Walk us through that, because standard transformers and even append-only looped models like RO calculate their KV caches in parallel during training, right?
Right. Because they only append new data, the calculations for token 1, token 2, and token 3 don't conflict at all. They happen simultaneously across the entire GPU array.
Which makes it incredibly fast.
Super fast.
Yeah.
But Melt's updating mechanism is fundamentally sequential.
Because of the dry erase board.
Yes. Token 2 needs to see token 1's finished, fully updated dry erase board before it can accurately proceed with its own calculations.
Oh, wow. So if you try to train Melt in a fully sequential, autoregressive manner, it would take an absurd amount of time.
It would be practically impossible. So to solve this training bottleneck, the researchers engineered chunk-wise training.
Chunk-wise training. Okay, how does that work?
They take the massive sequence of training data and split it into fixed-length chunks, typically around 500 tokens each. The computations inside that specific chunk utilize causal masks to run in parallel, which maximizes the GPU hardware.
But the single latent state vector, the dry erase board, is passed sequentially across the boundaries of those chunks.
You got it. It's a hybrid compromise.
So it balances training efficiency by keeping local parallelism while approximating the sequential nature it actually needs to function during inference.
Exactly. But the training hurdles, they don't stop there.
Of course not.
Training a 1.6 billion parameter model from scratch is prohibitively expensive. So the researchers actually initialized MELT using the pre-trained weights from Arrow.
Wait, they started with Arrow's brain, but you are taking a brain that expects to print receipts and forcing it to use a dry erase board.
Yeah, and the paper explicitly notes that due to the architectural changes and the newly initialized gating parameters, the model initially behaves like a completely untrained network.
It just freaks out.
Totally. It produces completely incoherent outputs right at the start.
So how did they salvage it?
They developed a highly specialized two-phase fine-tuning pipeline. Phase 1 is the interpolated transition.
Interpolated transition, meaning what?
Well, to prevent the model's pre-trained knowledge from collapsing, they compute both caches simultaneously during early training.
Oh, so it runs the standard Arrow append-only cache alongside the new melt dry erase cache?
Yes. And then it mathematically blends them. They use an interpolation coefficient called alpha.
Okay.
In the first training steps, alpha is set to 0, leaning entirely on the old KV cache. Gradually, they slide alpha up to 1.
That's fascinating. It's exactly like a DJ crossfading at a club.
That's a great analogy.
Like the DJ doesn't just cut the music abruptly to start a new track because the dance floor would completely stop.
Right, everyone would just stand there.
Yeah. So the system crossfades the mathematical weight of the attention mechanism smoothly over to the new method.
Exactly. But phase 2 is where it gets really strict, because even after the alpha coefficient reaches 1, the researchers observed that MELT's representations started to drift.
Drift away from the baseline knowledge it inherited from Arrow.
Yes. So to halt that drift, phase 2 employs attention-aligned distillation.
Attention-aligned distillation.
They freeze the original Arrow model so its weights cannot update at all, and they use it as a strict teacher.
Oh, I see. They apply an auxiliary alignment loss. They mathematically force Melty's post-attention representations to perfectly mimic the frozen teacher's representations.
At every single layer, across all reasoning loops.
Wow, it's like forcing an art student to trace a master painter's exact brushstrokes until the muscle memory is permanently locked in.
That is exactly what it's like, and it stabilizes the training and halts the drift entirely.
Okay, so let's zoom out for a second. You have a brand new learnable gate, a chunk-wise training fix for parallel processing, an interpolated crossfade, and an attention-aligned distillation.
It's a lot.
That is an enormous amount of theoretical and engineering gymnastics. So the ultimate question is whether all of this effort actually translates to a better, more efficient model when you benchmark it.
The short answer is yes. The memory savings alone are undeniable.
Let's look at the data. Let's return to our initial hook.
Right, so the paper provides exact VRAM requirements. If you want to generate a 32,000 token sequence, the original Arrow 1.4b requires 27.97 gigabytes of memory.
And 28 gigs of VRAM, for context, requires a specialized data center GPU, like an A100, or you have to link multiple high-end consumer cards together.
Yeah, it's not something you do on your laptop.
Ah.
But MELT 1.6b, performing the exact same deep reasoning, requires only 9.49 gigabytes.
That is massive. That is a roughly 3x memory reduction.
It fundamentally changes the game. It brings the memory requirement comfortably down to a single commercial graphics card. Or it easily fits within the unified memory of a modern laptop.
It achieves a strictly bounded, constant memory footprint, regardless of the sequence length.
Exactly.
Okay, so the efficiency problem is solved, but does the model lose its intelligence in the process?
That's the real test.
Looking at the performance benchmarks, MELT was tested against similarly sized, highly respected standard models that do not loop, right? Models like Qwen 3 1.7b, Gemma 4.2b, and DeepSeek R1 1.5b.
Yes, and the benchmarks focus heavily on multi-step reasoning. Tests like the AME24 benchmark,
which features questions from the American Invitational Mathematics Examination. Those demand highly structured logical deduction.
Right, and they also use the human evil coding test, which requires the AI to synthesize functional code from a prompt.
And standard 1.5 billion parameter models usually struggle heavily there without generating massive chain of thought output.
They do. But Melt consistently outperforms those non-looped baselines across the board.
So it is fundamentally a smarter model at that specific parameter count.
It really is. And the comparison back to its teacher, the original RO model, is particularly illuminating.
How so?
While Melt performs slightly behind RO on most mathematical benchmarks, but we have to remember, RO gets to cheat by using 3 times the memory to store its full prompt history.
Right, it has the handicap of massive VRAM.
Exactly. And despite that massive VRAM advantage for RO, Melt actually beats RO on the human evil coding benchmark.
That is incredible. But the researchers also included an ablation study in the paper, which I found fascinating because it proves why all this complex gating math was actually necessary.
Yes. The last loop disaster.
Right. They basically asked, what would happen if you skipped the learnable momentum gate entirely? What if you just took standard RO, and to save memory, you forced it to reuse the KV cache from its very last loop?
Yeah, so you attempt to share the cache, but without an intelligent, element-wise updating mechanism to manage the spectral stability.
And figure 4 in the paper details this exact failure mode. The model is given a prompt to simplify tan 100 degrees plus 4 times sin 100 degrees.
It starts off coherently, right?
It does. It starts discussing trigonometric identities normally. But because there is no gate managing the overriding process, the mismatch inside the shared cache accumulates rapidly.
The unmanaged spectral radius just breaks the model.
Literally. By the end of the trace, the model literally starts stuttering. It prints out, and I quote, let me see the angling in that. H maybe? H, wait, H, maybe. H.
It degrades into pure noise. The architecture just collapses into gibberish.
Yeah, and that stuttering proves you cannot just hack the memory by sharing the tensor array.
No, you really need Melt's dedicated, bounded dry erase board carefully managing what is kept and what is discarded.
So, bringing it all together, what is the ultimate takeaway for you listening to this deep dive?
Well, I'd say Melt is not just a clever engineering trick to save server costs.
No, it represents a fundamental paradigm shift in how we build AI.
It proves that we can achieve deep, iterative, multi-step AI reasoning without relying on a supercomputer's VRAM.
Exactly. By proving that complex logic can be strictly bounded by constant memory, it paves the way for sophisticated thinking AI to run entirely locally on personal devices.
And democratizing access to deep latent reasoning is really just the first step. The architecture inspired by Melt opens the door to a concept we can call adaptive loop depth.
Adaptive loop depth.
Right, because currently models like RO and Melt are hard-coded to loop a fixed number of times for every single prompt.
Exactly. They always loop the same amount. But consider the implications of constant memory.
Because the VRAM footprint stays exactly at 9.49 gigabytes, whether the model loops once or 1,000 times.
That's right. Memory is no longer the limiting constraint. So in the near future, the AI will dynamically decide how many times it needs to loop based on the inherent complexity of your specific prompt.
Oh, wow. So if you ask a simple trivia question, the AI realizes it requires minimal logic, executes a single loop, and outputs the answer instantly.
Exactly. But say you paste in a complex 500-line Python script with a hidden bug.
The AI detects the complexity.
Yes, it loops 50 times. 100 times. It churns on the problem, continuously refining its latent state, updating its internal dry erase board until it isolates the exact logic flaw.
And it does all of that deep, intensive computation under the hood without ever crashing your local memory. The compute scales dynamically to the difficulty of the task. The model thinks exactly as long as it needs to.
No more printing endless receipts until the cash register jams. Just a single, perfectly managed dry erase board holding the key to the next generation of AI reasoning.
It's definitely the future.
It is something to ponder as you watch the major AI labs release their next models. Keep an eye out for how they handle their memory bottlenecks because the days of the limitless scroll are definitely coming to an end.